I had to come up with a complex-sounding title, but this is about a real system, so it's not complex for its own sake. I tried to describe the parts of it. And it's a system we've been using for the past couple of years. What I'd like to do in my talk is give you a look into kind of a soup to nuts example of how Redis can be used to achieve very specific kinds of performance goals with specific features. So, I think it's an interesting talk for beginners to intermediate people. More advanced people might also find it interesting and take some ideas from it. Let me first take the opportunity to thank the organizers of this conference for giving me the chance to present this talk, and also my employer, Apple, for making it possible. I think Redis has been a really great influence on the open source community. It's set a very good example in terms of fostering strong engineering and not a lot of, how should I say, buzzword-based engineering. So with that, let me get started. A little bit about me. That's my Twitter handle. I've been working in software since 2001. I've worked at various companies, at Apple the past few years, before that Visa and AT&T. I've also worked with a lot of different startups, so I've kind of seen all kinds of things. I guess in my experience, you face the same kinds of challenges regardless of how small or big the company or the feature. It's very interesting. It's the same kinds of problems with different kinds of flavors. I've been using Redis since 2013. I really didn't know too much about it before then, and I just found it really fascinating how the documentation was so precise, and like it would show you the algorithmic complexity of commands, really encourage you to think hard about what you're trying to achieve. And allow me a shameless plug. I just finished a book on Ruby testing called RSpec Essentials. It isn't totally irrelevant to this talk. There's a lot of examples of how to use Redis, because when you're writing a book where you want to have real-world examples, it's very challenging to do anything that is easy to explain but also realistic. If you were going to use like a SQL database, there's so much complexity just explaining what you're doing, and you have to set up tables. On the other hand, if you make it really simple, it doesn't help people to solve real-world problems. But I found Redis was really great. You could have simple examples that would work in the real world. That's why I did several examples with Redis. And if you think about testing, how to set up your Redis database for testing, and little tips and tricks. So enough of my plug. So we're basically trying to build a message queue. SSH I/O streaming, the idea is to emulate a terminal session of SSH, but in an automated way. So you get basically the same thing you would see in your terminal if you're running it manually. The idea is we want a message queue that gets all that output. So how do we do that with Redis? It's actually pretty simple. Redis has PubSub, so you can set up a listener, subscribe to a channel, and all the bullet points with a little arrow in this slide are Redis CLI commands. So if you type Redis CLI, it'll drop you into a shell. So those are all Redis commands. And whenever something happens that's interesting, you use the publish command and you send a message. So the message would probably be something structured like JSON. There's some output from the command. This is the output, exit status. That will work. There's nothing wrong with that. And I'm all for brevity. Keep it simple. And I don't want to waste your time, so. Okay. I guess some people might get mad at that. A 2-minute talk, it's cute. And especially, I don't want to make Dodo mad. That's my Shiba Inu, by the way. There's more to it than that. How many pages? 3. including the table of contents. There's more to it. So the title is kind of complex. One of the words in there was persistent. There's no persistence here. If 5 minutes later I want to know what happened, there's nothing there. We have to do something to take care of that. And there's a lot of other specific details in terms of how to handle SSH I/O, and we'll get into that. First, let me read this quote. This is from Salvatore. It's an article he wrote about usage of Redis as a message queue, and it was actually discussing his new message broker system called DiskQ. Redis apparently is at the same time the best and the worst system to use like that. Like that means as a message queue. And I found it really fascinating because it really sums up my experience of using Redis for this feature. It's really great. You can do exactly what you want. When you run into dead ends with one approach, you can modify it without too much work and get it working. But it's also the worst system because you get something that is so tailored for your use case that it's a little bit hard to adapt when that use case changes. And throughout my talk, keep in mind I'm not actually promoting you guys to do something like what I've done. It's more to show you the processes that you kind of have to go through to get something working in the real world. And that's where it can be difficult to scale or adapt sometimes. But if your use case doesn't change, it's great. So we put this feature out a couple of years ago. The usage actually went up way beyond what we ever anticipated. We had some hiccups at the beginning, which I'll talk about, but it pretty much just ran. You know, when we ran into issues, pretty small tweaks helped us scale massively. So this is just the reality. You know, it's the best and the worst. It's up to you to decide, you know, whether it works for you. And I think that's actually a fundamental concept in engineering. The more highly tuned a system gets, the less flexible it's going to be. So if you take a very mature technology like an x86 processor, it's so highly optimized, it can be difficult to adapt it to a whole different use case. And you know, at some point, you need a radical new technology. So let me start telling you what the feature is. And I'll do a demo. First, I'm going to show you what this looks like in a web browser. So the idea, again, is to emulate a browser, a terminal SSH session in a web browser. So you see, I'm on a web browser here, page loaded. It looks kind of like an SSH session. There's a little bit extra. This is going to run in a loop, so it might be a little difficult to keep up. But the green is kind of like the prompt. It's showing you the username and the host. That can be very helpful. After that, you see a $sign and you see the command. The gray is basically metadata. You don't see that in a typical SSH session, but it's very helpful to get that idea, to get an idea of when things executed. If, for example, the sleep3 command took 80 seconds, we would find something went wrong. Often commands get stuck, and you know, I have a list of these commands that I'm running. This is just a random script. It doesn't really do anything. It just puts some output. You can see the red. That's standard error. At the end, you'll see some pink. Well, it's kind of hard to see here, but trust me, it's pink. The last message is telling you that the whole session finished. See, ran 6 of 6 commands. So that's pretty much it. We have a little drop-down where you could pick the host. So the reason we have this feature is we want to run commands on thousands of servers. And you can pick which one you see. There's a couple of subtleties that you have to keep in mind here. There's basically 3 use cases. One is I start the job and immediately I start watching it. So that's live. For that, we basically, that first slide with my Shiba Inu would be enough. You just publish live. The second use case is the job is finished, and an hour later, a day later, I come and I want to see what happened. That's where the persistence comes in. What drives most of the design actually here is a third use case where you come in the middle of the job. So the job has been running for maybe a minute. You come and you want to see what's going on. So you want to get the old persisted messages, and then once you get those, you want to switch to a live mode. So that requires you to basically splice these two streams together. Now, the browser is consuming a data feed over HTTP, and I'm going to show you what that looks like. So here I'm just using curl, and I'll tell you more about the job ID and the host name. You can see there's a keep alive. That's one of those things that you have to keep in mind. Sometimes a command can sit there for an hour. You don't know. So the browser would cut that connection. And then you get the data. The format is HTML5 Server-Sent Events, which is a very simple format. You have data, colon, space, whatever string, and then 2 new lines. The nice thing about HTML5 Server-Sent Events, I think all the browsers support it. You don't need any JavaScript libraries. You can consume a stream natively. There's built-in reconnect logic. It's very easy to use. It is one way, though. So this is one of those engineering decisions. A lot of people would use something like WebSockets, which gives you 2-way. That might be an interesting choice if you wanted to actually interact with the running session. But in this case, we're just viewing this output. One of the key considerations was to make sure this is secure. So with WebSockets and 2-way communications, now I actually have not I/O streaming, I have like basically SSH from the browser, which is potentially very dangerous. So you would have to put a lot of efforts to securing it, and you don't really accomplish anything by enabling that. We don't actually want people to go in their browser and start acting like they have terminal access. You can see that the messages are formatted in JSON. HTML5 Server-Sent Events doesn't care, it's just a string, so that's my own convention. And you can kind of get a sense of, see this one that's standard in, that's the command that was executed. This one's in the loop as well. You can see, oh, okay. All the messages have the standard in. So if you get a standard error message, you want to know what command that came from without having to somehow keep track of it. So little decisions like that help you because Redis itself is somewhat simple, and you can then display that appropriately in the browser. Let me talk a little bit about the architecture. There's multiple components. There's basically 3 parts to this. The first part is the SSH execution. That code is in Ruby. So we have what we call a job, which is a group of host names and a command. And we're going to run that command on all of those host names. For each of those host names, we have an SSH session. So here, I call the job A, and I call the host X. During that SSH session, we're going to capture all of the I/O. So the standard in this case, is the command that you pass to SSH. Standard out, there's a standard out stream that you can consume. There's standard error, it's another stream. There's also exit status. So we capture all of that, and we send it to the queue. So when I say send to the queue, that's kind of vague. I'll show you exactly what that means in terms of Redis. The important thing is we have this identifier, A:\X, the job and the host name. So that goes into Redis. At that point, we're publishing everything. Now we need to listen and get that into the browser. So all that code was in Ruby. we have a web service written in node.js. Ruby is not really good for event-oriented programming. The SSH library that we use is very unique. It doesn't look like any other kind of Ruby code. Node.js, basically everything is asynchronous and event-oriented, so it's kind of a natural fit. It allows us to listen for events and also deal with persistence. So what the Node.js web service does is it splices two streams. One is persisted data, one is live data. And it exposes it with a single interface. So even if you want to get old data for a week ago, you're going to get a live stream of HTML5 Server-Sent Events. That's another one of those design decisions. You know, you could basically say, well, if it's persisted, I'm just going to make it a regular HTTP endpoint. But the problem is the client doesn't know. If you have a job ID, how do you know if it's finished or not? So you would push a lot of logic into the client. And the client could figure it out. You know, they have multiple requests. But this is a lot simpler. There's one interface. And if the event is persisted, the stream is not really that different from a request response, a typical HTTP response. There is an issue when you have a very large list of messages. You have to handle that case in the browser. You basically have to optimize the code in the browser. It turns out that Redis and Node.js, they perform so well that the bottleneck is the browser. So you can easily crash your browser if you don't optimize. And basically, by optimize, I mean JavaScript set timeout. So basically, inject those set timeouts all over where you're consuming the stream and give the browser a chance to handle any normal tasks like updating the UI and not get hammered by the stream. We have a little authorization step that we need to make sure that the browser is authenticated before they can consume the stream. And then finally, we get an HTTP server-sent event stream. That's in the HTML5 spec. So the three parts, there's the Ruby part where we're executing SSH, the Node.js web service that converts the Redis events into something that the browser can consume, and then there's the code in the browser. All three are fairly modular. You have to know basically some of the conventions about how messages are formatted, but there's not too much interdependency between them. So now, let's look at how we build a persistent message queue with Redis. There's many ways of doing this. So this isn't the only way to do it. But basically, all we need is a list. We store messages in a list, and we pull everything. So my key would be that A:\X, a job and a host name, and we just get everything in there. If it's a live listener, that means the job hasn't started yet, then we'll get nothing, and we know how to handle that. The Node.js service handles that. If we get something that's not finished, there's a little trick we can play by looking at the last message to see if it's a session finished, and that's how we know it's finished or not. And when we publish, all we do is push a message into the key. It's very simple. So this is persistent. What about the live part? Well, it's the same as what we had before. We just do two different things. So we set up a live listener, and we retrieve persistent messages. And that's basically all that Node.js service does. It splices these two together. And the publisher now needs to do two things. You need to push the message onto the key, and then you publish the same message to a channel. We need a few other features to handle the SSH parts of the feature. So we would like to be able to look up by a session ID. So we have the job ID and the host name, A:\X, and I just want to get everything. This is basically just a matter of creating your own index. So what I'm trying to do is actually look up by job ID. So yeah, sorry about that. That should be job ID A. So I have an index that stores all those keys where the messages are stored. So whenever I need to get them, I can pull them. Now Redis has other features, like the keys command, but that's dangerous to use in production. So this is a pretty easy way of doing it. Often when you're using Redis, you can get away with not having your own custom indexes for a long time, but you get to certain features, you have to create your indexes. And you can get pretty much the same features you would get from a fancier database, like an SQL database, for smaller data sets and peculiar use cases. So you don't need to switch to a more complex database just because you suddenly need indexes. So that's just a list, and each entry in the list is a key name. For another cases, I have a host name. I want to know everything that happened on that host name. You know, you just want to get every job that was ever run. Something weird is happening on this host. You want to see everything. This is a little trickier. One of the considerations here is we want to clean up after ourselves. And we'll see more about this. But basically, these events will expire. Now, when we were looking up by job, each entry in the index could easily be expired because each key is going to be expired. So a job will expire basically at the same time. It's not like one entry expires earlier or later. When we're looking up by host name, by definition, this is happening over a long period. So the entries are going to expire at different times. We have a bunch of different jobs. So we need basically a way of expiring individual elements. And the way we accomplish that is by using a sorted set. And this is a fairly typical pattern. We use a timestamp, which is like the current timestamp. So we add the key of the session to this sorted set, and we set the current timestamp. So you see in the first example, I just tell it to expire after 604,800 seconds, which is 1 week. In this case, it's a little trickier. We've set the current timestamp, and then we remove everything that is before another timestamp. So if you take the first timestamp there and you subtract the second one, you'll get that same value of 1 week. So every time we add anything to the index, we remove the old ones. So this is kind of a typical pattern where you can keep things always clean. You don't have some other process coming in and cleaning up your indexes. You're basically cleaning things up on the fly. And there'll be more examples of that approach. Then what we need to do is wrap everything in a transaction. Redis has that facility just to make sure things happen in atomic units. Another major concern, kind of specific to SSH, we have to protect against excessive memory being used. So when the first day we launched this, and I worked on it for months, it blew up production within a couple hours. We were using 150 gigs of RAM. It turns out some of these SSH sessions have a lot of output, megabytes, hundreds of megabytes. Some of these commands were outputting the contents of a giant file. Some of them were download commands. If you imagine a download that gives you progress status, each time you get progress status, that's a message to standard out. And if it's running for 10 hours, you're downloading a gigantic file. Or the network's messed up and it just is sitting there. That's a lot of output. So we literally had hundreds of megabytes stored there. And you know, memory usage is one of the most important things you have to deal with when you're dealing with Redis in production. The way we dealt with that, it didn't require anything drastic. Each job would only have a certain number of messages. So basically, there's 100 messages. You only get the most recent 100 messages. So we're limiting the persistence. That will put a cap on the problem of having too many individual messages, the download progress. I could still have one message that's like a gigabyte. It's not hard to come up with something like that. that is still an issue. That's the last element there. So this would require you to do something outside of Redis and the Ruby code, keep track of how much output you're sending, and you just stop sending messages after a certain threshold. So once you get to like 1 million characters, that's it, we're done. And you just put another message that says truncated. And you just wait, and you put the session finished message at the end. Expiration is another way of dealing with this. So you need to make sure that these messages don't stick around too long, and that's based on real-world usage, so basically about a week. There are some types of jobs, some commands that are very wordy. Those get expired more aggressively, like about a day. These are all things you have to kind of tweak, and it's hard to plan ahead. Basically what you want to see is steady memory usage and kind of slow linear scaling, which we achieved. And we're running like, I don't know, tens of thousands of sessions a day, and the memory usage is around 10 to 15 gigabytes. It depends on what commands and some of the details of how those commands run. They change over time. But it's pretty stable. Like, there's no spikes of any kind. So here's what it looks like. So we have a transaction. We start that with multi. We push the message to the persisted queue. We set the expiration on the message to make sure that it doesn't stay around too long. We trim it. We trim it right here, not later on, because if we didn't wrap this in the transaction, we could have these spikes. If you imagine there's 5,000 sessions running and each is spewing a huge amount of messages, any kind of asynchronous cleanup would still give you these big spikes. And then you would be cleaning up an indeterminate amount. With this approach, if you think about it, we're only ever trimming one thing. We either trim nothing or one thing. So for the first 100 messages, there's nothing to trim. After that, we always add one, trim one, add one, trim one. So it performs pretty well. And at the end, we do the live publishing. I mentioned the indexes before. We only need to do this once. So, sorry. This is basically what each message looks like. Each message will have this format. I'll show you what the exact keys are and what the exact message is. For each job, we need to set up these indexes. And I showed you this before. Nothing really changed. The names of the keys and the channel is very important. Redis doesn't really give you anything in terms of organizing your keys. So it's up to you to come up with good naming conventions. And it's very important to start off with that and have good namespaces right off the bat. Otherwise, it'll become very hard to clean it up later, and you don't know what's in your Redis database. Things don't make sense. So it's a good idea to have a global namespace, in this case, SSHIO. I know basically this is this app or this feature. Then all of them have session. I think actually there's nothing but session. So, but maybe in the future we'd have something else like meta or some new feature. And there's not too much to them. So the persistent message queues have this format, event, persisted, and then you have a job ID, and you have the fully qualified domain name, the host name, basically. The live queue, this is a channel name. It's the same thing, except instead of persisted, you say live. The lookup indexes, session, event lookup by job, and then the job ID. It's all fairly logical. So you can look up what you need to. So this is a little different than if you have an SQL database, you run some command and you index some column name. Here you have to figure out how the index works. But it's really not that complicated. There's a last thing we do, which is a little bit ugly. And I think if you're doing real-world engineering and everything you're doing is shiny and smooth, there's a problem. Something's got to be a little bit ugly. Hopefully not too ugly. we'd like to know when a session is finished, and we'd like to know when it starts. And we want to do that in a simple way. So the way I do that, I have this basic key. I'm just going to write a blank string to it. And if it's there, that means a session is running. If it's not there, that means the session is not running. And I want to put a little bit of extra info in there. So in this case, we have session started, we have the ID. Now, it got a little ugly because I put in these ampersands. This is one of those ugly details. It turns out that our worker IDs have a colon in them. So the ampersands are there to get around that. Like, you're limited. You have a string to work with, right? So there's not much you can do. We could have tried to change the workers' IDs, but that's fairly deep code. And you want to easily basically be able to get that info that's variable out of that. So basically, we have an easy way of knowing when a session is running just by looking up a single key. And we can also have a live listener listening to key space events on that key. It's either going to get written or deleted. Nothing else happens. And so we have a way of knowing when sessions begin and end. And we use that to find stuck jobs, to do cleanup tasks. All right. So this is what it actually looks like. What I did was I started the Redis monitor command, which will show you everything that's happening in your Redis instance. And then I ran the feature, what you saw on the demo slide in the browser. And I captured everything. I only did a little bit of cleanup just to make it fit on the slides. Like, I shortened the IDs. But this is literally what you would see. So we set that started command to a blank string. These little details are important because when something goes wrong, you need to know where this code is being executed. That's why we have that worker. If you see the last part, it says fakeworkers.example.com. So we need to know which worker is executing this code. And the last part is the ID. So that's the process ID of this worker. If you don't put those little things in, it can be a little bit hard later to debug things. The rest of it, it's pretty much what we saw before, now with the key names filled in. And you can see there's that JSON format. We have a timestamp in each. We push to the list. We set the expiration, so the list will go away after a week. We make sure there's only 100 elements in the list. And then we publish the exact same message to the channel. And that's all a transaction. Here's the indexes. We set those up. Pretty much the same thing we saw before with the key names filled in. We have a job lookup index. We have a sorted set index. And then there'll be more of these. So this is another message. For each thing that happens in SSH, we're going to get one of these. And it's the same pattern. Multi, rpush, expire, ltrim, publish, exec. And you'll get a lot of these. Like, you get 20, 30 just by doing a couple commands. You get some more of these. And then the last one is a little special. If you see, it's the IO type is session finished. So the Node app and the browser look for that to kind of detect that the session is finished. We have another way of detecting the session finished as well. So there's a lot of overlap. You see everything has a timestamp. Things that are not strictly necessary, but they don't hurt to be there. One of the problems we had, though, was there was way more stuff in each message. There was this metadata that we were automatically capturing, and it was like 10 times the size of the actual message. So this isn't a particularly efficient serialization format. You could do better, but really what was hurting us was all that extra metadata. And once you start looking at the raw command, you're like, wow, what is all this stuff? I don't need these keys. You just take it out. Compressing this is actually not going to help that much. Each message, there's not that much to compress. What would be nice is if you compressed the whole list, because then you get like 10 times compression factor. That's hard to do, though. There's no like compressed list feature in Redis. It could be done. You could have a background job basically do that. Maybe someone will create a compressed list module now. But it's not really needed for our case. Like, we're using like 15 gigs of RAM. It could be really useful, though, in the long run, because the expiration of 1 week limits what this feature can be used for. We can't use this for long-term persistence. If we could set an expiration of 3 months, we could get rid of a whole bunch of other systems. But 3 months, if you think about that, that's like 12 weeks. So we need to do a lot better. Like 12 times 15, it's going to be 180 gigs of RAM. That's getting kind of high. I mean, we'd need specialized hardware or a cluster. It makes things a little complicated. So, for our use case, it hasn't made sense yet. Also, long-term persistence with Redis is kind of not an obvious choice either. It's an in-memory database. At the end, we do this delete event to signal that this session is over. That's basically so we don't have to look up the list, look up at the last element, and see if it has an IO type of session finished. So anything that's dealing with this queue doesn't need to know about the serialization format to know that the session is finished. Let me give you a little bit more. This is a Lua script that does a lookup by host name. So basically, we have this sorted set that has a bunch of keys in it. Each key has a bunch of events in it. We want one command that's just going to give us all of that. And it's going to be in order per host name. So if you look at the sorted set, the index, this is for a particular host name. So fakehost.example.com. You see that contents, it's a little hard to see. That's supposed to be green. Man, I should buy one of these projectors at home. I'll know what the colors are. Each entry is just another key to the persisted queue. So it's pretty simple. It basically is going to do a nested table. There is a little weirdness because of a conversion between Lua and Redis. But what's cool is Redis documents this. You don't have to go searching on Stack Overflow to know about this particular detail. And this is not particularly complex Lua code. We just loop over everything in the sorted set, and we call lrange for each of those. You could do this outside of Lua as well, but then it's a matter of how much of that logic you want to put into your app. And the Node.js app already has some pretty complex logic. So drawing that line is important. The more you can put into Redis, the better. So you don't have to have all this complex stuff outside. And if you execute this, this is more like running Redis CLI from the command line. Let's say we have the file in values from lookupset.lua. We run the eval command. You have to tell eval how many key names you're going to pass to it, in this case, 1. So it's one of the interesting things about Redis is the way you run scripts, you have to differentiate between what input is a key name and what input is not a key name. And that's what allows it to perform very well. And the key name is basically our host name prefixed by something that's static. So if we're looking up everything for fakehost.example.com, we just append that namespace to it. And then we'll get this nested list. See, the first is that key and its contents. And then a whole bunch of 18 more of those. Then the last one is that key and its contents. So these are all different sessions that ran on that host. And it's pretty easy to process this. It's just an array of arrays. I mentioned authentication. So the browser directly talks to this web service, and we need to authenticate that the user's been logged in. And we use Redis for that as well. So when you log in, the web app creates a token for the Node.js service, and it writes it to Redis. You might as well, why put it some other weird place? So Redis is the shared state between the web app and the Node.js web service. And we put that in the browser session. There's a 1-day expiry, so basically every day as you log in, you'll get a new one. And all that's done with a little Lua script as well. So basically, whenever you log in, we execute this Lua script for you, get the output, and put it in your browser. And it's pretty simple. Again, this could be done outside of Redis, but it's another one of those things that it's nice to just have this one command that does it all for you. It really doesn't do much. It's basically is a, I think it's a get set x. At the time when we wrote this, I don't know if that command exists now. Another idea for a module. If it exists, just get it. If it doesn't exist, set it and also set an expiry. So it's not that complicated. You just want to do that all atomically. And when you run it, the first time you run it, it stores it. So this wasn't set before. And again, notice the namespace, the username is at the end. Session, stream, auth. The second time, if you notice the second one, I'm trying to set a new token. But it's not going to let me because it already exists. So if we go back to the overall architecture, there's this common message format. It starts in the Ruby part of the code. And the same format gets all the way out to the browser. So I mentioned earlier on that the kind of critical performance issue was all in the browser, actually. I was expecting this thing to break if too many people were trying to use it, if too many sessions were happening. It actually works really well. The problem is when you try to get something by host, or there's actually a fire hose option where you get everything on every host. What breaks is the browser or curl. And the interesting thing is that we didn't really do too much to make this highly performant. The only real issues that we addressed were memory usage. And we put in a lot of specific things to deal with that. But in terms of performance, we did do a lot to generally optimize our Redis usage, looking into our persistence options, our replication options. Those helped a little bit, but performance was fine. And we're running a single master with a slave. The main problems we tend to see are spikes in network I/O when replication happens. And that's kind of a tricky thing to get right. A lot of the performance optimization was in the browser. So the demo you saw, basically, it's an AngularJS app. And AngularJS has some nice features to allow you to handle asynchronous data in kind of a clean, easy way. You basically have a loop, and as you get things from the stream, it just draws it for you. But it turns out that's called ng repeat. That's like the worst performing feature in AngularJS. And it just hung the browser. The fix was to put in a few of those timeouts I mentioned. But what we did was we went ahead and just wrote the stream part of it in raw JavaScript. And it's a little bit clunky. You have a lot more calls to create an element, to mess with a DOM, but not too much more. And that performs super fast. I mean, the problem was actually just being able to see the output and make sense of it, because you get so much of it. So that fire hose doesn't really make sense for a human. Maybe an automated system could deal with it. And if you compare this feature to other solutions, like with Logstash or Splunk, those have certain features that we needed, but they didn't give us an easily consumable stream into the browser. And one of the main things we wanted to do is be able to show the standard error and the exit status and the timestamp. I think the best thing about this is it really forces us to be engineers and design a system, understand the components, instead of being consumers where we buy a product or we install a product and we spend all our time configuring from the outside. We had to kind of build this out. And I think it put us in a position where we could think about how to build this with Redis or without Redis. And I think that is what's really great about Redis. The educational process, it forces you to be very sharp, to understand every command and design things for yourself. So thank you for listening. And I want to let you know that no Shiba Inus were harmed in the making of this presentation. Thank you.